So basically, we were moving on with an exercise. We have a 2D element. And we can make use of the image we have yesterday, of the save of clarity. We'll recap some of the noteworthy relationships that we developed yesterday. Okay. So again, just to recall, here we were in the process of developing and obtaining the definition of the mass matrix that we, in fact, completed yesterday for the element. Again, we have an element composed of two nodes and of a 1D formulation. This is a Euler beam. In this frame, this is a formulation that we are developing in the frame of the floating frame formulation. So we have the intermediate frame I1 and I2, Ij. In this case, it's just a 2D space, which is parallel again to the element frame I1 and I2. Here it is. And it has a certain orientation with respect to the body frame, okay, which is constant because we have an approximation that we have introduced in our formulation in which the intermediate frame is initially parallel to the element frame, and then it maintains constant its orientation with respect to the body frame, which we have in here. So we have B2 and B1. Okay, so the basic relationship that we developed yesterday basically linked, if you remember, the position of a point with respect to the body frame as a matrix N, depending on Nij, where I is the subscript associated to the body and J is the element number, acting on the vector of nodal quantities Nij. Okay. In particular, we can also explicit a little bit further this relationship, because we know that within this N, in fact, we have two additional matrices, C1 and C2, okay? Which we're going to recall in here. So we have C2, Ij, C, Ij, and C1, Ij, okay? Where C1 and C2 are the matrix which describe the orientation of the intermediate frame with respect to the body frame, and C is the element shape matrix. Huh? Okay. So this is basically where we arrived. We were able to derive all of the relationship for the element frame with respect to the mass matrix. Today, what we are going to see is the derivation of the stiffness matrix. Okay, so we're going to have the derivation of the element stiffness matrix, and in so doing, we resort to, let's say, a strategy that we have already seen, and we will expand further here today. All right, so as usual, when we think about the stiffness matrix, we think about the elastic energy associated to the body, no? So the potential elastic energy to the body, in this case, has the very familiar formulation, which we are already aware of. which is of the sort which I'm going to recall in here. Okay, in the X1. Okay, you can see here that, as usual, we have two terms. The first one here is the axial rigidity of the beam. In fact, we have the Young's modulus and the cross-section of the beam. And then the second term is associated to the deformation, so the bending of the beam. And as we have already ascertained in many cases, the axial deformation is associated to the first-order derivative of the displacement induced by deformation, and the deflection in the transverse way is associated to the bending with the second-order derivative. Okay. Here, in theory, I should, in order to avoid using the subscript I and j, I can also directly put it here, okay, on the top of this, the square brackets, meaning that here E and A and W, they are all ij, because they are all the stiffness and the cross-section and the moment of inertia of the element. Okay, they are characteristic of the element. All right, from here, we can elaborate, because we know that, as I was recalling in here, that Rij is, as we have seen, Nij, Qeij. But then Qeij, which is the vector nodal coordinates, can be again expanded as the sum of two terms, Q0ij, which is the value of the nodal coordinates before the start of the deformation process, and Qf0ij, which is, again, the value of the vector nodal coordinates induced by the deformation. This being said, we can say that the term Nij applied over Qf0ij is what we have called W, okay, which is the counterpart of U, the letter Uij, which we use for the overall body. Okay, so again, what is this? This is a formula which describes the dependence of the displacement induced by deformation for each point within the element with respect to the values at the nodal at the nodes. Okay, and we can refer to this so that we can further expand these values here. Okay, so this one here and this one here, okay, is what we want to expand here. Okay. Any question? Okay. So let's elaborate a little bit more on this. And from here, we can continue writing the following, as we have said already, this is Cij, C1ij, Qfij, okay? Where these again are the shape functions. Now, if this is true, what we need again is not directly the displacement, but its derivatives. Okay, so we can eventually disentangle the two components, 1 and 2. Again, they are only 2 because we are in 2D case. can put ij again on the outside of the bracket. And here we can basically denote as a prime and a double prime the single and double derivative of w1 and w2 with respect to the space coordinate x1, 0. Okay, you see here we have again the first order derivative for the axial deformation and the second order derivative with respect for the transverse. So this is what we have, okay, to develop. How can we now express these two quantities that we have to substitute within the integral, resorting, making use of this? Okay, let's do it. Again, in this relationship, which I've already developed, the only dependence on space coordinates is on the relationship integral. So this is to keep in mind. All right. So again, we can write the following. So C2 ij, okay, and then we have C1, which is the first row of the element shape matrix ij, and then we have C2, which is the second row. Okay, we are resorting to the typical notation that we have used so far. And then we have C1. But in this case, we have a prime to be adopted over the first row and the second prime to be adopted on the second row. Okay? Again, because this is just a consequence of what we need to develop. Okay? Again, because the space dependence in this writing is only ascribable to the element shape functions. Okay, and then again we have, of course, the final vector, so ij. If you remember, we had that C1 ij was nothing else but the following. Then we had a 0. This we have already introduced at the start of this exercise, if you recall it. Okay, so this was the first, this is the first row, if you want. And then we have the second row, which is a little bit more long to write, but let's do it for the sake of clarity. Let's recall it here. So we have a 0, the very first element, 1 minus 3 x1 over L to the second, plus 2 x1 over L to the third, and this is the second element. Then we add x1, 0 minus 2 x1, 0 squared over L plus x1, 0 over bar to the third over L squared. Then we have a 0. And then we have 3 times x1 overhead over L squared minus 2 x1, 0 over L to the third. And this is the fifth element. And then allow me to go a little bit further. x1, 0 over bar over L squared minus x10 squared over L. Okay, ij. Okay, so again, as you can see, we can check if this makes sense. Okay, so this is a column vector, so it's a 2 times 1. This we know it's a 2 times 2, huh? Because again we are in the 2D case. This is a row, and it's a 6 times 1. This is a 6 times 1. So this is a what? Sorry, this is a row, so it's a 1 times 6, and this is a 1 times 6. So this is a 2 times 6. Okay, and it fits. And this is a 6 times 1. So this means that eventually we get what we were expecting. Okay, please do not get confused. So this here, they are rows. They are row vectors, as in fact we have seen here. Okay. This time, as you may have noticed, I didn't use the xi notation for the rows, but I explicitly wrote the dependence on the x coordinate, because eventually I wanted to underline that here, in this expression of the elastic potential, we had a derivative with respect to the x. Okay, so eventually we have to derive these two vectors. And it's a straightforward thing to do because they are two polynomials of up to the third degree. Okay. So this means, to sum up, that we can write the following. Putting all together, our elastic potential is 1/2 on the integral from 0 to the length of the element j, of the body I, of what? Of q f0 ij transposed, applied over c 1 ij transposed, times what? Times psi1, the vector prime, so derived one time, transposed, okay, meaning that this is now, since it's transposed, it's a column vector. And now you have psi2 double derivative transposed ij. Okay, and then we have c2 ij transposed. Then we continue here. Well, we have to put inside the axial stiffness and the transverse stiffness of the integral. Again, the ij superscript, I will be placing them on top of the matrix for the sake of clarity. Okay. And then we have to basically rewrite the non-transposed counterpart of what we have already written. That's to say, C2 ij, not transposed. And then we have C1 prime, not transposed again, C2 double prime, ij. Okay. And then we have C1 ij. Okay, and finally qf0 ij. All of this integrated with respect to the x1. Okay, now you see again that if we highlight the quantities within this integral which are actually dependent with respect to the space coordinates, we have only again this. Okay, this is a constant eventually term, but we can retain it. And then we have here. Okay, so for sure we can put outside of the integral sign this and this. Now, what about instead these two matrices here? We know that they describe a rotation, so they are orthogonal matrices. Meaning that when I'm going to multiply this term to the stiffness matrix, and then I multiply the result to this, eventually what I'm going to get is an elision of the contribution of this and this. Okay? Because again, we know, and I can write it here, C2 ij transposed applied over C2 ij, or even the transpose of this, is the identity matrix. Okay? Identically. Meaning that basically this and this I can just cancel out. Okay? So if you rewrite all of these equations, just putting outside the quantities which are not dependent on space and canceling out the matrices which are orthogonal, you eventually get the following. Of what? C1 prime transposed C2 double prime transposed ij times EA 0, 0 EI ij applied over C1 prime C2 double prime ij in the x10, all of this being multiplied by C1 ij and QF0 ij. Okay? And this again can be finally written as 1 over 2 of QF0 ij transposed times K ij ff times QF ij. Okay? Where this quantity here has been condensed within this matrix. Okay, which is again the stiffness matrix that we were trying to develop. Okay. In particular here, you can say that KFF ij is the structural stiffness matrix of the element. Okay? Any question? All clear? Okay. All right. So again, in this case, there is something which is different from what we have seen so far. Because in the stiffness matrix, we have also encompassed two terms, C1, okay, the C1 matrices, which are variable with respect to the orientation. So until now, we always have dealt with stiffness matrices which were constant. In this case, instead, there is a variability associated to the angle of rotation. Okay. In particular, to be honest, in the approximation that we do, C1 is a constant matrix as well, because, again, the angle that is included within the C1 matrix is the constant angle beta, okay? So here we have beta, as we have seen yesterday, and also in here. And in the linear approximation that we have done so far, that we have adopted so far, this angle which describes the neutral orientation of the intermediate frame with the body frame is constant in time. So again, in this case, KFF in our approximation is constant, but typically it can also be variable. Okay. All right. So if there are no questions, this basically concludes this section of the course. And then we approach to the last one, which is kind of short, which will be, let's say, which will focus on different techniques to reduce the magnitude, the order of the models, when we basically have to deal with numerical models which are very, very large. Okay, for example, this is the typical case for numerical applications, in which we have a lot of degrees of freedom, and we have to reduce this number, still retaining the information that we deem necessary for our analysis. Okay, so when you reduce the number of degrees of freedom, you always pay a cost. Now, the important thing as an engineer is to see if this cost is affordable for us. We can afford this cost. Okay. And for this reason, there are different techniques that can be adopted depending on the approximation that we want to introduce. So the new topic, the last basically topic of the course, is coordinates reduction techniques. Okay. Have you ever heard of this? No? Okay. So these are quite useful, both from a numerical point of view and a theoretical point of view. So we typically implement these techniques on discrete or discretized models. The difference between discrete and discretized is that a discrete model is naturally discrete, okay, like a spring mass damper, okay, system. Discretized is typically a continuous system on which we have implemented, for example, a restricted formulation, and that, as a consequence, becomes discretized. Okay, so it's not naturally discrete. So we can write it down. So typically, adopted on discrete / discretized models. the consequence, the outcome of this technique is a reduced order model. And typically, we refer to these models as ROMs. Okay, reduced order models. The idea is that we have typically three occasions, which are ideal for the application of these techniques. Okay, so the first case, when we have an interest in investigating a reduced, a limited bandwidth of frequency in the response of the structure. Okay, we do not want to know the response of the structural system on the overall bandwidth of the frequency. Okay, but just in a very specific narrow region of the frequency axis. Okay, so interest a limited frequency bandwidth. Okay. And so again, this already gives you the hint on the use of these techniques, because again, if we are interested only on one part of the spectrum of the response, maybe we can sacrifice, okay, the rest, the accuracy on the rest, reducing the number of the degrees of freedom. Okay. Then the second case in which the adoption of such techniques is ideal, when we can subdivide the structure into different parts, okay, and we can condense, we can condensate some of these parts into what we are called super elements, and then we will make a hint to this. Okay, so basically what we do is, okay, one part is not very important, for example, a rigid element, okay, and then we condense this element and the degrees of freedom which are associated with that element into a super element, and again we will see what this is, which has a reduced number of degrees of freedom. Okay, so body composed of multiple parts. And the third case is basically when we have a system composed of multiple bodies. Okay, so it's basically a generalization of the second item. So in the second item, we have a single body divided into different parts that we want to collapse into smaller models. The third case is when we have multiple bodies into the system, and this is a typical case for multi-body applications, when we want to collapse, to reduce the number of degrees of freedom associated to certain bodies which we have not too much interest into investigating. Okay? So model composed, multiple bodies. Okay, but
Prof,
can
you please explain the second one again?
Sure. So imagine having a body, okay, and for example, let's say that you have a plane, Okay, or for example, you have a satellite composed of solar panels. Okay, now let's say that you are not very interested into investigating the dynamics of the solar panels. So you can collapse the solar panels to a single body, which is the core of the satellite. This will allow you to reduce the number of degrees of freedom of the body and lighten up the resulting numerical model. Okay? So you still have one body, but the total, the overall number of degrees of freedom has been reduced. Okay? On another point of view, in the item 3, you reduce the number of degrees of freedom of a body within a collection of bodies, still retaining, again, the difference between the different bodies, okay, which will eventually be connected somehow, okay, through a certain boundary condition or constraint equations, okay? So the difference between the second and the third item is that in the second case, you have only one body. In the third case, you have a collection of bodies. In the first case, you collapse, you reduce a portion of the body. In the third case, you reduce or collapse a body within a collection of bodies. Okay?
Okay, Prof, thank you.
Sure. All right. Okay, all of this is very theoretical if you want. Let's put our hands on the concept. And the concept is the following. First of all, let's just make clear let's be clear on the notation. So, we will consider, without loss of generality, that we are dealing with a body which is properly constrained, so a single body which has no rigid degrees of freedom. Okay, so simplifying hypothesis, no rigid degrees of freedom. Okay? As a consequence, our MFF, okay, which is the structural mass matrix, we will denote it just as M. Okay? And our structural stiffness matrix will be denoted just using K. And our vector of elastic coordinates will be denoted by Q. Okay, just, you know, to ease out our notation. All right. Now, again, the idea of the reduction techniques. So the basic idea of reduction techniques. What is it? So we have a vector of nodal coordinates, which is n times 1 as a dimension, the original. And somehow we want to pass to a new vector of nodal coordinates, which we can refer to as Q. I think we use R, yes, QR as a subscript, so reduced, which is an m times 1 vector with m smaller than n. Okay, this is the really simple idea. And this is the reduced again. Now, how can we achieve this? Well, the techniques that we are going to see today and in the next lecture will encompass linear transformation. What is a linear transformation? well, it's a transformation which encompasses either multiplication or sum, okay, operation. In particular, we will search a relationship of this sort in which Q, the original Q vector, is equal to R, a matrix R, applied over QR. Okay? So we are going to search for a relationship, a linear relationship, as you can see, because this is a matrix, in which we can reduce the number of the nodal coordinates from n to m through the use of a matrix. Okay? So this is going to be, again, an n times 1. This is an m times 1. So this is eventually an n times m matrix. So it's not a square matrix. Okay. So this is in time. It's in time domain. The same relationship can be used in the frequency domain. Okay. How can we pass from the time domain to the frequency domain? What is the typical transformation? Fourier, or Laplace. Laplace and Fourier. One is actually a subcase of the other. Let's see Fourier. Okay. And we are going to denote the Fourier transformation with a hat on the notation. Okay, so basically like so. Okay. So this is basically denotes the Fourier transform of the time counterpart. Okay. So, or is in the frequency domain. So it's a very easy, eventually, at least the one that we are going to explore, very easy transformation. So frequency domain. Okay. Now, can we always apply this? Well, no. There are some hypotheses that have to be fulfilled in order to apply this kind of transformation. Okay, let's see what they are. Well, we have HP1. Identity of kinetic and elastic What does it mean? Well, the elastic energy in the original model, we know already, because we have seen it so many times, that has this form. Okay. While the kinetic energy has a similar notation. Okay. This is in the original formulation. In the kinetic formulation, in the reduced formulation, sorry, you can denote it UR. This will be, quite not surprisingly, written like so. And, of course, the same goes for the kinetic energy. Where Kr and Mr are the reduced mass and stiffness matrices. Well, if we want to reduce the order of the model, we always have to guarantee that the reduced model retains the same kinetic and elastic energy. So it means that so the following must hold: that UR is equal to U and TR is equal to T. Okay. These two conditions eventually, given the definition of the relationship that we have between Q and QR, leads to the definition of the KR and MR matrices, okay? Because we have two equations here, and here we have two relationships. We can use them to derive MR and KR, okay? In fact, in here, if you substitute to Q this relationship here, if you have seen, and you do the same also in T, you will have the definition of KR and MR. Let's do it, sorry, for the sake of clarity. So, U is 1 over 2 of QR transposed R transposed K R Q. Okay? And this must be equal to UR. But UR is this one. Okay? So it means that this must be KR. Okay? And the same goes for kinetic energy. In fact, already in this expression, we can elaborate, something on this transformation matrix R. What is it that we can deduce from here? That when we do the derivative of Q, it only derives QR and not R, the matrix, meaning that R does not depend on time. So this is typically something that holds true. Okay? So that the transformation matrix does not depend on time. Okay? All right, so this is the hypothesis number 1. Then we have another hypothesis. Can I turn the slide? Okay, so hypothesis number 2. The hypothesis number 2 is that we are going to subdivide, okay, the model, the overall number of degrees of freedom of the original model, into two different classes of coordinates. Master coordinates.
Scusi, prof, non so se solo a me, ma si è bloccato lo schermo. Cioè, non so se sono solo io.
No. Just a sec.
Grazie.
I think we have to restart the Blackboard, so just 1 minute of patience. I will do it. We have to restart the Flipboard. Hopefully this will solve the problem. Okay, let's try again. Okay. Can you see now? I will slide back to the previous part. Okay.
Grazie.
Okay. Sure. So again, the second hypothesis, simplifying hypothesis that we're going to make is the one that will subdivide the overall number of coordinates into. Non c'era segnale? Ah, okay. Well, this is the cable which, is not of the maximum quality possible, but I think it's going. So we divide it into master and slave coordinates, and the idea is to relate the slave coordinates to the master one, so that eventually we only deal with the master and the slave will follow. Okay. So if you want, the reduced vector, so our QR, will be the vector of master coordinates, okay? And the slave will be basically embedded in our formulation, okay? But there is an hypothesis in doing so. Let's see what it is. So we divide our Q vector in a master and a slave part. So basically we're going to make a partition like so. Q, which is an n times 1, is typically dividable into a Qm and Qs vector. Okay. Now, the condition that we have to satisfy is the following. No external load will have to insist on master nodes. Okay. So if you have external forces, no external forces will have to be placed on the, on the slave nodes. Slave nodes. Okay. If it has a force on top, it cannot be a slave, it has to be a master. Okay. So you can think about it in the following way. Imagine a wing, okay, of an airplane. You can, for example, you can collapse all of the nodes of the wing on the root nodes of the wing, okay? But then you have to make the hypothesis that the forces insisting on the wing are not placed directly on the nodes of the wing, but only and overall on the nodes which connect the wing to the fuselage, okay? Otherwise, you cannot do this collapse. We will see it on Monday. Yeah? But this is just to make an example. So this is the second hypothesis. Okay. This being said, the next step is to consider the equation of the dynamics of a system to see how we can implement this partition. Okay. So dynamic equations. Well, this we have seen so many times. Let's see the simplest case, okay? So we have the mass matrix. Then we have the acceleration. Then we have the stiffness term, QF. And then we have a vector of generalized external forces, okay? Or in frequency. M over hat, Q over hat. When we do the Fourier transform of a doubly derivative of time, what is that we miss here? Oh, huh? Di che cosa? Of what? Yeah, the angular velocity. Yes. Exactly. So that's the Fourier transform, right? Like so. Okay. All right, now let's rewrite this, resorting to the partition, okay? Yeah, there is no signal now. It comes and goes, it's true. Fortunately, the connection between the flip and the PC are not the best, but this is what we have. So, all right. So again, let's just introduce this partition in our formulation. Okay. So we can basically subdivide the mass matrix as such. You can write M. So let's not use too much space. So M master slave, M slave master, but we know that this and this, they just must be equal, because we know that the mass matrix is symmetric. It's a symmetric matrix. Then we have QM double dot, if we do it in space, in the time domain, sorry, plus the same thing, but for the stiffness matrix, KMM, KMS, KSM, and KSS. Okay. And then eventually we have our force, which we can write please notice that in the vector of generalized external forces, I've put a 0 on the rows of the equation associated to the slave nodes. Because again, in the slave nodes, as an constitutive hypothesis of this model, there must be no loading, okay, operating. So this is the time domain. We can write exactly the same in the frequency domain. So we put a minus in front, an omega squared as a multiplying term, scalar multiplying term, and then we can do exactly the same. M with an overhead, denoting the fact that we are dealing with a Fourier transform quantity. All of this can be summed to the second term, the stiffness term, again here we have the Fourier transforms. Okay, all of this multiplying the vectors of the Fourier transforms of the nodal coordinates equal to the external forces, again as a Fourier transform. Okay. So this is the frequency domain. So these are the typical equations of the dynamic of a structural system that we have seen plenty of times so far, no? In all of the courses that you have attended. Now we can rewrite. We will make basically use only of the second term because it's easier to stay in the frequency domain to treat the time derivatives associated to the acceleration only with a multiplication of a constant term, of a scalar term, sorry. So let's rewrite the second, okay? So second system can be rewritten as such. We have two equations. KMM operating over QM overhead plus K MS over QS overhead minus omega to the second operating over MM times QM overhead plus MS QS equal to F overhead. So this is just the first row of the previous matrix equation. Okay? I've just written it in a plain way. The same goes for the second row. So we have K Sm over hat Qm plus K SS Qs equal to omega squared times MSM Qm plus MSS Qs. Now you see, if you observe these equations, what you get is basically a relationship between the master and the slave nodes. Okay. What we do is resorting to this, and for the sake of clarity, we can enumerate these two equations. We can indicate this as A and this as B. So equation A and equation B, because we will make use of them quite often in the following. Now, so this is the frame into which we are going to build our technique to reduce the number of coordinates. Okay, we have built all these frames. So the hypothesis for the use of these techniques is, first, conservation of elastic and potential energy, kinetic energy. And second, the fact that there has to be no load insisting on slave nodes. If these are respected, then we can build on. The first technique that we are going to see today is the static condensation, also called Gaian iron method. Okay. Is this familiar to someone? No? Okay. So, static condensation. And since it was introduced by simultaneously a guy called Iron and by the name of Gaian, so they were two engineers, you can also find this technique as referred to as Gaian iron condensation. So aka Gaian / iron method. You can already have a hint at what is the idea of this static condensation. So we denote the slave vector of coordinates in two parts, always in the frequency domain. A static component, QSS, plus a dynamic component. Okay? So, as you can imagine, by definition, the static component is the part of QS which exists when the frequency is 0, right? So the static term and QS, the dynamic. Now, if QSS and QSD, yeah? If QSS is the static term, what we can try to do to derive it, you can rewrite equation B here with an omega equal to 0. If we put omega here equal to 0 in equation B, it means that we are in the static case, no? Let's do it. And let's see what is the value in that case for QS. Okay. So in the static case, omega equal to 0. Equation B becomes as it follows. K SM QM, okay, which is the master part of our coordinates, plus K SS times Q S S, no? Only the static part, equal to 0. Okay. In fact, what I did was only to rewrite equation 2, basically eliminating this part. Okay, you have this one. Okay. Why did I do that? Because I can, using this equation, resort to an equation which gives me a link between the master and the static part of the sleeve. Okay. Remember that my goal here is to build a relationship which connects the reduced vector and the original vector coordinate. So here I'm just already building up a relationship between the static part of the slave and the master. Okay. So QSS is minus KSS to the minus 1 by to KSM all of it insisting over QM. In particular, we typically denote this as a new matrix S QM. Okay. We basically just denote this minus KSS to the minus 1 times KS is a hat, like S. So this becomes this. Okay. Now we can rewrite always equation B for the case of omega different from 0, so the original one. Okay, so we are going to rewrite this equation, but introducing the last definition. Okay, this one here. So we rewrite equation B introducing the matrix S. If you do it, you get the following. K as S minus omega squared MSS multiplying the dynamic part of the slave vector equaling omega squared M SM minus M SS applied over our S matrix. Okay, all of this being multiplied by QM. You see what I got here? I've got a relationship between the dynamic part of the slave vector and the master vector. Okay, so this is the second part that I missed. Okay, so in this equation here, I already got a relationship between the static part of the slave vectors and the master nodes. Here, I'm getting a relationship between the dynamic part of the slave vector and always the master node. So eventually, if I put together all of this, I'm getting a relationship between the slave nodes and the master nodes, which is what I deserve, what I was actually searching for. Okay, so this means that our QSD, so the static part, is quite straightforwardly to the -1 of omega squared MSM okay. So here is the first one of the relationship that we needed. And here is the second one. Now, in Gaian iron method, so that's why it's called static condensation, we say that this QSD part is 0. Okay. Take your time to write. So this is the founding hypothesis. So the founding hypothesis of Gaian iron method, which is called static condensation for a reason, is to neglect the dynamic part the slave vector. That's to say, the QSD is equally identical to 0. Okay. But then, what is the meaning of this? When is it actually acceptable, again, to do this approximation? And here we come back to the idea of averaging pros and cons, okay, of a method. So if we say that the dynamic part of the slave nodes is 0, it means basically here that this coefficient between QM and equal is equal to 0. And when is it that this is equal to 0? When the first part here is equal to 0. And this is an inverse of a term. So it means that the direct part, so the one between round brackets here, this one, must be very large. If this is very large, its inverse is very small, and therefore all of this is basically 0. And what is the meaning of having this term very high, very large? It means, so this is, as you can already recognize, this is the eigenproblem associated to the slave part. You see, it's the eigenproblem. So the static condensation makes sense when the dynamics of the slave part is at frequencies, happen at frequencies which are not of interest for my study. Where if I study the dynamic of a part whose slave nodes have a dynamic which is much higher than the bandwidth, the frequency bandwidth that I'm interested into, then I can safely consider this basically equal to 0 without losing information that matters to me. Okay, and then you can safely use the static condensation. Okay, so this means using this means that KSS okay, and so I can conclude, and then we end here the lesson. Can use the Gaussian iron method when the dynamics of the slave part of the model take place at frequencies much larger than the bandwidth, the frequency bandwidth of interest. Okay, this is when you can use the Gaussian iron. So tomorrow, it's actually not tomorrow, next lecture, so on Monday, we're going to see how this result will allow us basically to build that R matrix, which links the original and the reduced part. Okay. So, unless there are other questions, this is all for today. So I will close here the lecture.
Arrivederci.
Arrivederci.
Arrivederci.